G'day guys, welcome to exercise 76. So in this example we're looking at the addition of some vectors. So to start off with, we have an aircraft travelling at 200 knots with a heading of 47 degrees from true north. Okay, the wind, so a second vector or a second force being applied to our aircraft, is the wind blowing from 330 degrees with a speed of 20 knots. So in the example given, they get you to draw the example, which is roughly what I've got drawn here, but I haven't actually drawn it to perfect scale, so I can't really just measure it. The way I teach this is to calculate it out using the individual vectors. So the red line there is the addition, i.e. nose to tail, of the two vectors that I intend to add. The two yellow lines that I've just drawn up there are the first vector, so our blue line just here. That we can just work out as a right angle triangle to give me my two components, which are the two yellow lines we've drawn there. My second triangle, or my second vector that I'm adding on, I again can look at that as a right angle triangle using the two pink lines that I've added on there. So the final triangle, which is the right angle triangle involving the red line, or that red vector, is going to be my final vector to try and get a hold of. So essentially what I'm going to do is, along the top, I'm looking at that line there plus a little bit more of that one there, which is these two vectors up the top. And then for going down, what I'm looking at is my initial vector coming up, and then this one here is going to oppose it, coming back that way, leaving me with my final vectors of this one here, which represents that one there, and this vector here, which is the addition of those, which represents that one there. Okay, that's what we're aiming for. So in order to achieve that, what I would have to do is to get the values for these two, for all four of these vectors around the outside. So looking at this one here, so my blue and yellow triangle, I'm going to start with that one, and I'm going to go and label it. So H is my hypotenuse. If that's the angle that I've got, so theta, that will be my adjacent. This will be my opposite. Okay. Sine theta equals opposite over hypotenuse. So essentially, I can plumb my values straight into there. So sine 47 equals my opposite over my hypotenuse. Sine 47, if I go to my trig table, is 0.7314 divided by 200 being the length of my hypotenuse there. So transpose that across to the other side, and I'll have 200 times 0.7314 equals opposite. Therefore opposite will equal 146.28 meters. Okay, so that's essentially this component here. is 146.28. Okay, so then I need to work out my adjacent. Again, we'll do that for the blue and yellow triangle first. So cosine theta equals adjacent over hypotenuse. So from there, put my values in. So cos 47 over my adjacent over my hypotenuse. So put my values in there, and I will get 0.6820 equals adjacent divided by, adjacent divided by 200. So if I flip that over the other side, I get 200 times 0.6820 equals my adjacent. Therefore, adjacent equals 136.4 meters. So I really just need to find the values of the green and pink triangle there, or the two vectors that add up to make that one. Okay, so I'll sketch this one down here. So on here, I know if this was coming at a heading of 330 degrees, so that was the direction that my wind was coming from, this angle in here will be 30, which is essentially 360 degrees minus 330 gives my angular difference in here of 30 degrees. Okay, so again, my hypotenuse equals 20, and I need to calculate my opposite and my adjacent. Again, I'll start with sine. Sine theta equals opposite over hypotenuse. So sine 30, because of 30 degrees, equals opposite divided by 20. So 20 by sine 30 equals the opposite. If I go to my trusty trig tables, that leaves me with 20 times 0.5, which is the value for sine 30, equals the opposite. Therefore, it's going to opposite is going to equal 10 knots. Okay, so from there I'll go to cosine. Cosine theta equals adjacent over hypotenuse. So cos 30 equals adjacent over 20. So 0.8660 equals adjacent over 20. Again, we can flip that over there, so 20 times 0.8660 equals my adjacent. Therefore, adjacent is going to equal 17.32 knots. Okay, so now that I've got those two values there, I can add them on here. So this is a clean 10 knots here, and this one going in the opposite direction to my original vertical is going to be 17.32 knots. So, because these values now are directly opposing each other, we can simply add them or subtract them to give us the values required for our purple here. So 146.28 plus 10, that's going to leave this one here at 156.28. So because this one here is in the opposite direction, or it is directly opposing that one, I'm going to take my 17.32 knots off my 136.4, leaving me with this component of my vector is going to be 119.08 knots. Okay, so effectively where we're at now is we now have that component there and that component there, being these two values drawn up the top here. So using them and a little bit of trigonometry to get the angle, and a little bit of Pythagoras perhaps to get the distance, or sorry, the speed in knots, or the length of that vector, if you will, that will see us at our final answer. Okay guys, so I've just redrawn the final vector on a new diagram just down below. Notice again that I've got my north, south, east and west, or my cardinal points. My easterly component, as we worked out before, is 156.28 knots. My northerly component, or my vertical component on this picture, is 119.08 knots. Okay, so I guess I'd probably start with the length of this. So if we think to Pythagoras Theorem, C equals the square root of a squared plus b squared. So if I use these two here, so 156.28 squared plus 119.08 knots squared, find the square root of all that, and I cheated, I used the calculator because I was trying to work it out a little bit faster, and I ended up with 196.47. Of course, if we were doing this for the exams that you guys are sitting, we're going to be working that out by hand. Okay, so I now have the length, or the strength, or the airspeed of this line here, which is going to be 196.47 knots. All I really need to do now is to work out my heading. Okay, so given the information I have, I can work out this angle in here using tan. So tan theta equals opposite over adjacent. So if I look here and I call this theta, this would be my opposite, this would be my adjacent. Again, hypotenuse would be up there. So from there, tan theta is going to equal 119.08 over 156.28. That worked out before as 0.7620 with a little bit of rounding in there. So from there, I'm going to just have a quick look at my trigonometry table. Once I find that, if I find there, tan 37 is 0.7536, which it's basically halfway between my 37 and 38 degrees, so I just went with 37. So from there, we're going to call this tan 37 degrees. Notice that the angle we've calculated is in this part. So if I was actually looking to try and find the heading, I need to have that with respect of true north coming back this way. So essentially what I'm going to do is have my 90 degrees. So the reason I'm taking it away from 90, because these two angles in here would be complementary between my cardinal points. So 90 minus my 37 leaves me with 53 degrees. So when all is said and done, the aircraft's track and heading, which is what we were after, will be 196.47 knots at a heading or track of 53 degrees.